Okay, next we move to filter design. Alright, so for you to design a filter, you need to refer to the given specification. Okay, so and then based on the specification, you need to transform all the given information into tolerance diagram. So based on the tolerance diagram, you may know what type of filter you need to design. Okay, so basically, as I mentioned before, we have 4 types of filter, right? So we have low pass filter, high pass filter, band pass, and band stop. Okay, so again, I want to emphasize again, all those filter is designed based on the given specification. Okay. Alright, so for the first step to design filter, you must really understand, okay, what type of filter you want to design. Okay, so as we know, okay, we have 4 types of ideal filter. Okay, let's say we have low pass filter. So basically, here is your low pass filter. If you look at this graph is actually your ideal filter, and this ideal filter is impractical in real life application. So I name this filter as our desired filter. Okay, so this filter is named as our desired filter or desired impulse response. Okay, so based on our desired impulse response, we need to design the filter. Okay, so as you know, for you to get the real signal, in real signal, we cannot have the ideal signal. Okay, why? Because of our signal, our real signal is actually the smooth signal, means we have variables value for the magnitude, for the amplitude of the signal. So basically, it is impractical for us to get this kind of signal. Alright, so what we have to do is, okay, we do inverse Fourier transform. Why? Because of all our signal is basically in time domain. So what you have here is actually in frequency domain. Okay, and then you must know, in practical, okay, in practical signal we have 2 problems. Okay, one is on infinite time, another problem is on non-causal condition. Okay, so basically, here is our problems. Here is the practical signal problems. So basically, for us to design the filter, we need to solve the problem. So how to solve the problems? I'm going to show you here. Alright, so basically, we have a signal. For example, this signal in time domain. Okay, not in frequency domain. Why? Because we already do the inverse Fourier transform. Okay, next we're going to have our signal. Alright, so here we're going to have the repetition signal, which to show that it is periodic signal. Okay, why? Because of this is the discrete time signal. Okay, alright, so if you look here, this signal is actually the practical signal. So if you look at this signal, it is infinite time signal, means the signal is from minus infinity to infinity. So because of this one, we need to solve the problems. So how we are going to solve the problem? Okay, so solution for infinite time. For us to solve infinite time, we need to do windowing. Okay, so what is windowing? Windowing means we select our important information, our important signal. So let's say we select this part. Oh, sorry, this part. So basically, if you look here, this is our window. Okay, this is our selected information. So here is basically our window. Okay, so we select our window from -m to m. Alright. Okay, so next we need to solve the non-causal issue. So basically, how to solve our non-causal issue? We need to bring our important signal to the right. Okay, if you look at this signal is considered as two-sided signal, right? On causality, okay, the signal is causal if the signal is right-sided signal. Means you have to bring all the signal to the right. Okay, so when you want to move the signal to the right, means you have to do what? You have to do time shifting. So if you want to do time shifting, or in other words time delay, you need to shift your signal, this signal, to the right by m. Why m? Because the non-causal, the signal is non-causal. The cause of the non-causal is we have a signal from -m to 0. So we want to move this part to the right by m. Okay, so basically to solve this non-causal, we need to shift. Now, after you do the windowing, after you do time shifting, so next you will get this kind of signal. Okay, just now we do windowing, right? So windowing because of we want to select our important signal. Okay, so this is our important signal. Okay, so what happened? Okay, we have our important signal. Okay, so this is our important signal. Okay, and then why it is at the right sided? Because of we already shift. Okay, we shift the window, the selected information, to the right by m. Okay, so now we have this kind of signal. Okay, so basically m is your the shifting numbers. Okay, if you look here, we have n. That's why in the formula sheet we have 2 plus 1. So basically, capital N is your length of sequence. Alright, so if you look here, this is actually in time domain. If you want to see the signal in frequency domain, you need to do D, T, D, F, T. Okay, so what you will get is like this. Okay, your magnitude, your frequency, and then okay, if you remember, for our ID filter, we have low pass filter. So what happened? We're going to have the low pass filter, but in terms of practical signal. Okay, we're going to have like this. Okay, so here is our passband. Here is our stop band. Okay, so the value is, okay, for this one, the value is delta S. Here is 1 minus delta P. So next, we are going to have our omega P, and then we have our omega S. And from here also, we can determine our delta omega. And from here also, we can have our cut-off frequency. Alright, so if you look here again, this is actually your tolerance diagram.